next talk is Xavier Ros-Oton from University of Barcelona. And is it online?
Yeah, hello.
Yes, okay. So Xavier Ros-Oton is a specialist in elliptic PDEs, interpolated parabolic fractional PDEs, fractional Laplacian, fractional Prof equation, and some related questions. So please, Xavier, you can start here.
Thank you very much for the invitation and for the introduction. So I will talk about joint work with Alessandro Audrito and Juan Carlos Felipe-Navarro. And this concerns a Neumann problem for the fractional Laplacian. So let me start by explaining a bit the context. So as you all know, we are interested in studying interdifferential equations that come from Levy processes. And then the kind of operators we would be interested on are operators of this kind. So linear translation invariant and elliptic operators, okay, that have a kernel here. And then the typical assumption is that the kernel is comparable to the one shown here, which is a power minus n minus 2s when s is between 0 and 1. And then the most canonical example is the fractional Laplacian. And this is what I will assume in this talk. Okay, so throughout this talk, I will assume that the operator is the fractional Laplacian, but actually many of the results that I will present are also valid for more general operators of this kind under this assumption. Okay, but let's focus on the fractional Laplacian for simplicity. So for the Laplacian, for the classical Brownian motion and the Laplace operator, we have two problems. On given a bounded domain, we can consider two different problems, right? The Dirichlet problem, which is imposing, say, 0 on the boundary. Function is fixed on the boundary. And the Neumann problem, which is that the normal derivative is 0 on the boundary, right? And then these two problems come from the same energy functional. Okay, so there is a variational formulation to both of these problems. And in both cases, you have this natural energy functional to consider here, okay, where f is the right-hand side. And then the Dirichlet problem is the one that you obtain when you minimize the energy functional among all functions in H1, satisfying the Dirichlet condition, u equals 0 on the boundary, right? So when you minimize the energy with the fixed boundary condition, you get the Dirichlet problem. Instead, when you minimize the energy functional among all functions with no restriction on the boundary, then you get the Neumann problem, right? So you minimize among all functions, then well, you need to, I mean, this is defined up to additive constants, but say that the average is 0, and then you get the solution to the Neumann problem. So this is just to remind you of this construction of harmonic functions in domains under either Dirichlet conditions or Neumann conditions, because now we will have an analogy with the fractional Laplacian. Okay, so what happens for non-local operators? Well, the Dirichlet problem is very well studied and understood, and the Dirichlet problem for a non-local operator of this kind is to impose your equation inside the domain, right? Fractional Laplacian of u equals f in omega. This is the equation that is satisfied inside the domain. And then the Dirichlet condition must be posed everywhere outside the domain, because this is a non-local operator, right? So you have u equals 0 everywhere outside omega. Okay. Now, the associated energy functional to Dirichlet problem of this kind, because here you can put u equals 0 or u equal g, of course. You can put always a non-homogeneous Dirichlet condition as well. And then the natural energy functional that is associated to this problem is this one. Okay, so the energy functional is basically the double integral of, the HS energy. Okay, but you don't integrate the outside omega. Of course, when u is 0 outside omega, this is the same, but it's important when you consider more general non-homogeneous conditions. So this is really the natural energy functional for the Dirichlet problem. Okay, given a domain omega, you minimize this, then you get the solution to the Dirichlet problem. Okay, and then when s goes to 1, this converges to the integral of the gradient inside omega. So this is really the natural energy functional that corresponds to the Dirichlet one, also when s equals 1. Okay, and then, as I said, you take this functional, you minimize this functional among all functions that vanish outside omega, and then you get the solution to the unique solution to the Dirichlet problem. Okay, and then once you have constructed the solution, you can study the regularity properties. Okay, how those solutions behave near the boundary, for example, in the interior, and then the regularity of solutions is nowadays very well understood. And then you can see, for example, my paper with Joaquim Serra, but then there are also many papers due to Jet Group and many others that have, and now basically the boundary regularity, the interior and boundary regularity for this problem is very well understood. Okay, so this is the Dirichlet problem. Now, what is the Neumann problem for the fractional Laplacian? Well, if you take into account the analogy that I presented before with the Brownian motion and the Laplacian, then you find the following Neumann problem. Okay, so the Neumann problem for the fractional Laplacian turns out to be something like this, or at least a Neumann problem for the fractional Laplacian turns out to be something like this. So you have the same equation inside omega, and then you have a Neumann condition, a non-local Neumann condition everywhere outside omega. Okay, and what is this operator ns of u? So this is a non-local Neumann derivative in a sense, and it's given by this. So for your function you take this integral. So you compare u of x. So remember that x is outside omega, and you integrate u of x minus u of y for every y inside omega. Okay, and then with the kernel of the fractional Laplacian. This is the Neumann, the non-local Neumann operator here. Okay, and then I claim this problem is well posed, and you can prove existence and uniqueness of solutions up to additive constants. And then this is done with the same energy functional as before. Okay, so let me explain this a little bit. So this is a non-local Neumann normal derivative, as I said, and this is the problem that we studied in a joint work with Serena Di Piero and Enrico Baldinocci. And then these kind of problems have been studied before also in this paper. Okay. So this is a very natural Neumann problem. And why is this? Well, so some basic properties. First, it has a variational structure. As I said, so solutions are obtained by minimizing this energy functional, which is the same energy functional as in the Dirichlet case. You minimize this energy functional among all functions, say with average 0, and you get the solution to the Neumann problem. So in terms of, from the point of view of calculus of variations, this is the natural Neumann problem for the fractional Laplacian. Okay, and then it also has some nice integration by parts formulas. So for example, this is very easy to prove. You just take the integral in omega of the fractional Laplacian of a function u, any function, and then this equals the integral outside omega of this non-local normal derivative. Okay, and in addition, you can have also a more general integration by parts. So this would play the role of the integral of gradient. Okay, in this case, this is a bilinear integral, bilinear form, and then this quantity, this should be a double integral. Yeah, this is, equals to the integral of fractional Laplacian of u times v plus the integral of v times this non-local normal operator. Okay, so you have some variational structure, you have some integration by parts formulas, and it also has a natural probabilistic interpretation that we, so basically we introduced a heuristic probabilistic interpretation in our paper with Serena Di Piero and Enrico Baldinocci that has been later studied more from the pure probability point of view. And this interpretation is basically, you have the Levy process inside omega, and then when the process exits the domain, it goes back inside with a certain probability distribution. Okay, and then you at least heuristically, this gives you this Neumann problem with this variational structure. Okay, and then you consider the heat equation, it has conservation of mass. So as S equals to 1, it converges to the classical Neumann problem. It has all these natural properties that you expect from a Neumann problem. Okay, so in the Dirichlet case, what is the regularity of solutions? Well, the regularity of solutions in this case is the following. So you have an example, and solutions behave like a power of the, say, near to the boundary, it behaves like the power s. Okay, so it's like comparable to the distance to the power s, this function. Okay, at least in the unit ball. And then it's a infinity function, but it's cs up to the boundary and not better. Okay, and this is something that can be proved in general for general right-hand sides and general domains. And this is what we did here in this paper. And solutions are cs up to the boundary. This is optimal. And then solutions are always comparable to the distance to the s in the sense that u over distance to the s is Helder continuous. Okay, so this is the Dirichlet problem. Now the question is, well, what can you say about the Neumann problem? Can you prove something like that? What is the optimal regularity of solutions? Okay, so for the Neumann problem, all these questions are delegate, and inside omega solutions are infinity, or at least as smooth as the right-hand side allows. But even some basic questions were open after our paper with Di Piero and Baldinocci. And the first question is, well, are solutions even bounded or continuous up to the boundary? Okay, so proving that solutions were continuous up to the boundary remained open for some years. And then the natural question is, well, if they are Helder continuous, then what is the optimal alpha? Okay, so first, are they Helder continuous? And then what is the optimal alpha, or what is the best estimate you can prove? And here, several difficulties arise in the sense that compared to the Dirichlet problem, there are no explicit solutions to this problem, not even in dimension 1. Okay, so if you try to prove the optimal or to guess what is the optimal regularity of solutions, or if they are continuous or not, well, you don't have any explicit solution, basically, not even in 1D. Okay, and then classical methods, when s goes to 1, you flatten the boundary and you do an even reflection. All these kind of techniques don't work in the non-local case, so you cannot use any techniques from the Neumann problem for the Laplacian. And the methods from the Dirichlet problem in the non-local case don't work either, because they are based on barriers, because you have the boundaries fixed and then you can use sub and super solutions. This doesn't work here as well. Okay, so these are the difficulties in order when you try to answer these questions, to prove that solutions are continuous or to prove that solutions are Helder continuous with an optimal exponent. Okay. Now, in a recent work, I mean, this was a preprint a couple of years ago that was has been now accepted for publication, and we proved this result. Okay, so in particular, we answered these questions. So the assumptions that we need are very mild, I would say. So the domain needs to be only C1, and the right-hand side simply bounded. Okay, and then under this assumption, and the right-hand side can even be in LP. Okay, and for some P's. So under these assumptions, then we prove for the first time that solutions to this problem are indeed continuous and Helder continuous for some small alpha positive. Okay, and so this is the first time in which we get an estimate like this. So we get an estimate, say, for all solutions under these assumptions. And in addition, whenever S is bigger than 1/2, okay, so now we need, at least in some cases, when S is bigger than 1/2, we can improve this Helder continuity to get something a bit better. And we get that solutions are 2s minus 1 plus alpha, okay, for some small alpha positive. Okay, so if S is close to 1, this implies basically that this is almost C1 alpha. Okay, so that solutions are classical, they solve the classical Neumann condition as S goes to 1. Okay, and the same holds, so both results hold as well when F is in LQ, whenever Q is bigger than N. Okay, so for any Q larger than N, there exists an alpha so that this happens. Okay, so this is our result. Okay, so this answers the question of, well, continuity of solutions, Helder continuity of solutions, and then we also find like this exponent that I will explain briefly in a second. Why do we find this exponent? So this is the first regularity result for this Neumann problem. And recall that even the boundedness and continuity of solutions was not known. And the boundary regularity turns out to be much more delicate than in the interior. Okay, and this is something that we already see in the Dirichlet problem. So when trying to understand the boundary regularity for non-local equations, this is quite delicate and quite different from local equations, and turns out to be much more delicate. And to prove the result, what we do is to introduce a Moser iteration on the boundary. Okay, so Moser iteration is a classical technique for elliptic PDEs, but this is to prove interior regularity results. Well, here we use this in order to prove a boundary regularity result for a non-local equation. And our Moser iteration, so this had been used by Kasman and to prove interior regularity results for non-local equations as well. But we use it here on the boundary. And this Moser iteration has some logarithmic corrections on the boundary. So this is quite non-standard, I would say, because it's not really a classical Moser iteration, but everything has logarithmic corrections on the boundary, and this makes the problem quite tricky. And then, so this is to prove the C alpha estimate. So with this iteration, we prove that there exists a C alpha estimate for some alpha positive, for some tiny number alpha. We have that solutions are C alpha. Okay, and this is like the first half of the paper. Okay, and this holds even for Lipschitz domains and for every S between 0 and 1. And then the second part of the paper is to improve this. And this is where we find that this exponent 2s minus 1 is somehow critical for the problem. Okay, so it's not that there are solutions that are of this power, but this power is somehow critical. And then it's good that we can pass from this exponent, and we pass from this exponent in the sense that we prove that for S is bigger than 1/2, we prove that solutions are C 2s minus 1 plus alpha. So we get a bit more than this exponent. Okay, and this is done with a completely different argument. So using this C alpha estimate, we can run a contradiction and blow up argument, okay, by compactness, and we get that we find this exponent that is found in dimension 1, and we pass from dimension 1 to any C1 domain in a red. Okay, so basically, if we can do something in dimension 1, our methods yield that the same is true in every C1 domain of a red. Okay, and then basically this problem of 2s minus 1 is what appears in dimension 1. Okay, so when you are in 1D, you already see this 2s minus 1 appearing. And even in 1D, it's not clear to us what is the optimal regularity. Okay, so if you try to answer what is the question of what is the optimal regularity, well, you first have to answer it in dimension 1. Okay, and then basically, so we develop all tools that are needed in order to get higher regularity results. And this is the estimate that we prove. So basically, this is the question that you want to answer. Okay, so if you will improve our result, all the methods and techniques are built in our paper, essentially. Okay, but if you want to improve this exponent here, you need to answer this question. You need to prove a Liouville theorem in dimension 1. So if you have the fractional Laplacian equals 0 in a half line, and then the normal, this non-local condition, Neumann condition in the other half line, and then you have a function that satisfies this with some growth at infinity. Okay, and then this growth is beta in dimension 1, remember? Then I want to prove that then this implies that the function is constant. Okay, so if this was the Laplacian, so if you put s equals 1 and this is the normal derivative at the origin, then you do an even reflection, and this is true for any beta you want. Okay, up to beta equals 1, because then you get up to beta equal 2, sorry. Okay, but then in the non-local case, this turns out to be very tricky. And then what I claim, I mean, what we prove is that if you have this theorem for a certain beta, then you have this estimate for the same beta. Okay, in all C1 domains of a red. And then what happens is that we can prove this theorem for this exponent beta equal to 2s minus 1 plus alpha. Okay, this is what we do here. And it's an open question to decide, to determine if this can be improved in higher, to higher powers beta or not. Okay. So this is a natural and nice question that remains open for this Neumann problem. And then in the last minutes, I wanted to mention that there is also another natural Neumann problem, which is when you consider the regional fractional Laplacian. So if you consider the regional fractional Laplacian, you get a different Neumann type problem, okay, which is to consider this other energy functional, which is integrate in omega times omega. So you take the double integral in omega omega. So this is an operator that is defined only inside omega. So you have no condition outside omega because you get an operator that sees nothing outside omega. So everything lives inside the domain. Okay, so this can be natural also in other situations. And this had been also studied before, but not much was known for the Neumann problem for this operator. So here you have as well two classes of problems. You can have the Dirichlet condition, okay, which is fixing u equals 0 on the boundary. And this makes sense when s bigger than 1/2. And you can have the Neumann problem, which is valid for every s between 0 and 1, and is minimizing simply this energy functional freely for free functions, say in HS. Okay, so if you consider this different problem, which is the regional fractional Laplacian, this is the corresponding operator, which is like the regional fractional Laplacian that is integrated only inside omega. Then the Neumann problem has also a probabilistic interpretation, conservation of mass for the heat equation, convergence when s equal to 1 to the classical Neumann problem. So you have the same motivations, and it turns out that from the point of view of our proof, they are basically the same. We can treat both problems at the same time. And what we do is to prove the same result for this Neumann problem as well. Okay, so in our paper, we prove the same theorem that I presented before is true either for this, for the first Neumann problem that I presented, or for this other Neumann type problem, which is the regional fractional Laplacian. Okay, so in both cases, we get exactly the same result. And interestingly, in our paper, we got the same power, 2s minus 1 plus alpha. Okay, and now, so this was our paper, okay, that was a joint work with Alessandro Audrito and Juan Carlos Felipe-Navarro. And more recently, together with Mustafa Fall, we studied this problem. So first, Mustafa Fall had a paper in which he improved our result, okay? And he proved that the power 2s minus 1 plus alpha can be improved to 2s minus epsilon for every epsilon, but only in case of the regional fractional Laplacian, not in the other one. And then more recently, together, myself and Mustafa Fall, we proved in a preprint that in the regional case, in this regional fractional Laplacian case, okay, and this is something that we don't know how to prove, or if it is true for the first Neumann problem that I presented, but at least for the regional fractional Laplacian, what we proved is that solutions are C2s plus alpha up to the boundary, and that this is optimal. Okay, so we find the optimal alpha for which this is true, and this alpha is a number that involves some gamma functions. Okay, so this is an explicit computation that can be done in dimension 1, and the reason for this is that in dimension 1 we can understand completely what happens in this case. So the Liouville theorem that I said before for the regional, but now for the regional fractional Laplacian, we can study it with the extension problem. Okay, so we basically extend the function by 0, and then we do a nice trick that was found by Mustafa Fall in his previous paper, and then we can understand completely what happens for solutions to this Neumann problem. Okay, and then we can find that in all domains in higher dimensions that are smooth enough, the domain needs to be C2s plus alpha, we prove that solutions are indeed C2s plus alpha with the optimal alpha, which is explicit. Okay, and so basically this is all I wanted to say. So I'll be happy to answer any questions you have. Thank you very much.
Thank you. Are there any questions? And for people not from this room, please unmute yourself, introduce, and ask question again. Yes, please.
Already some questions that you already got somewhere else. So if you can give us some physical intuition on the boundary conditions that you are imposing in the Neumann generalized Neumann problem. Of course, we know where the Neumann problems arise in electromagnetism, etc. And here, what could be a system to which you could apply these conditions?
So there are these two. So first, this one had been studied before. This is like a sensor process. So let me explain for both of them. Okay, for the regional Laplacian, this is what it's called the sensor process, which is a process that basically is it can jump, but it can jump only inside omega. Okay, so this is easy to study in a sense from the but this is not a Levy process because it's not translation invariant, and then the operator is this one. Okay, so this is a process. This is a stochastic process that can jump, but it is imposed that it jumps only inside omega. Okay, all the time. And then the other problem that I introduced, this one. For this one, when you have the domain, our heuristic interpretation is that whenever you can jump anywhere, so at any moment of time, you follow the same Levy process as for the infinitesimal generator with the fractional Laplacian. But if for some instant of time it jumps outside the domain, okay, then you impose that the particle automatically at the same instant of time is coming back inside the domain in a random way. So you only impose something when the particle jumps outside. Okay, and it's not a reflection because if you jump very far outside the domain, it's not a natural way to. I don't see a natural way to impose that there is a reflection on the boundary, right? So instead of a reflection, it's a kind of you impose that the particle comes back inside, and then the point at which the particle comes back inside is not determined deterministically, but just randomly. Okay, and then this is the interpretation I have, and I don't know where to apply it other than, this is what we did. We introduced this problem that has a natural, or at least for us, it was a natural interpretation of this Neumann problem that arises when minimizing the energy functional. But I don't know where it can be applied. So this is a matter of modeling that I guess other people can study. I don't know if this answers your question or not.
Yes, it seems so. Thank you, Javier. And let us thanks again. Oh, there is one more. No, okay. No time. And okay. So the next speaker is Vanya Wagner from University of Zagreb of beautiful Croatia, and